Okay, so good afternoon, everyone. So today we move to the new topic, interpolation and least squares approximation. So before I start the topic, let me run a simple program in MATLAB, okay? And so now let me share my screen, yeah? So suppose you can see my screen now. And suppose I run program. I think this one is available on in Moodle as well. So suppose I run a simple MATLAB program. Okay. So think. Suppose I want to plot my hand. Okay. So suppose I want to do some graphics program that simulate the movement of my hand. So now the first step is I try to put my hand into the program. Yeah. So how do I do that? Well, maybe I put my hand on the screen. Maybe you don't see it, but suppose I just click on the coordinate of the points that on my hand. Okay, and I just trace through it. So maybe now you don't see anything, right? So, but let me just click on the points that trace in the curve that somehow plot my hand. Okay, so you will see it for a moment. So maybe let me choose more points. So you see, so this one is just a simple graphic user interface. So I move the mouse according to the contour of my hand. Okay, and I click on the curve that trace through my hand. So now let me finish. Okay, so you see that on the screen, you see roughly, you know, I've traced through my hand. I mean, it's not a good pictures, but at least you see the principle, right? So on the blue dots are where I hit the enter. I mean, I hit the left button of the mouse, yeah. And then, you know, after the program collect on the blue dots, then it will plot the red curve. Okay, so then the red curve trace through the contour of my hand, right? And this process we call it interpolation. Okay, so that is the process interpolation, and they use it a lot in computer graphics, you know, computer games and so on. So and this one is just a simple graphic user interface. So now go back to the slide. So now I will so let me go back to the slide, yeah. So I will introduce what is interpolation, and there is two famous mathematicians, you know, associated with the two forms of interpolation. One is Lagrange, is a French mathematician, and Newton. So everyone knows Newton, right? So Newton has contributed to interpolation problem as well. And then, you know, later on, after we study interpolation, okay, so sometimes you cannot have the curve that fit the data exactly. Then we have a least square approximation. So that is the last part of the whole chapter. So now maybe, so I did this one already. So I just traced through my hand, and you saw the interpolation process in practice. So now, so if you remember, you know, the simulation, so the data points are the blue points. Okay, we label it as xj, yj. So for example, the blue points on the Cartesian plane, you just take the coordinates of those points. Okay, then you label it as xj, yj. j run from 1 to n plus 1 point. So suppose you have n plus 1 points, okay? And then the curve. So remember the curve, right? So in the example I show you, the curve is not a interpolation, it's not a polynomial. But let's take a very simple case. Suppose you have a curve. What is the polynomial? Okay. And if you remember the definition of polynomial, it's like 1 plus x squared, something. So it's like polynomial, okay? And then the polynomial interpolates the data. So it means that the curve goes through the blue points, okay? So if you plug in xj to the polynomial p, then you get yj, okay? And so now we don't have any information about derivatives. We just have the information, you know, that it goes through those points. Okay. So now suppose, now take a simple example. Suppose I have 4 points, x equals 0, y equals 2, and x equals 1, y equals 0, x equals 2, y equals minus 3.
Recording in progress. I am a computer generator.
Det roliga är att den har liksom Zoom, för Zoom är kinesiskt.
Ja.
Den har en kinesisk så här, liksom brytning typ.
Anyone? Okay, I just mute everyone. Okay, so now go back to this example. So how do you find this polynomial? How do you find this polynomial? So what is a cubic polynomial? Use a general form. So what is a general form? Okay, so a general form, you make a general polynomials with a, b, and c, and d, and you solve the simultaneous equations. Yes, very good, very good. Okay, so at least you know what to do, right? So you have, at least you know one way to do it. So you have 4 unknowns, a, b, c, and d, right? So you write ax squared bx squared plus cx plus d, and you plug in the values. Okay, x equals 0, x equals 1, so on and so forth. Then you have a system of, you know, 4 by 4 equations, 4 unknowns and 4 equations, and you solve it. Okay, so that's very good. But, you know, Lagrange, you know, he's a French guy. He said that, okay, I can do better than that. I don't need to solve any equation. I don't need to solve any linear equations. So how did he do that? Okay, so now look at what he did. So he defined L1. Okay, so L1 is defined to be a cubic of this form. So you see that, remember you have x equals 0, x equals 1, x equals 2, x equals 3, right? So here you have x minus 1, x minus 2, x minus 3. Okay, and then, you know, I mean, the very first one, you ignore that. So x equals 0, you don't have it. Yeah, so you don't have 0, but then you put 0 down here. So this is the first x. Okay, the numerators again. So the numerator is, you take x minus every point except the first point, and you multiply it. Okay, so remember you have x equals 0, x equals 1, x equals 2, and x equals 3, right? Yeah. Okay, and here you ignore the first point. This is ignore x equals 0. Then you take x minus 1, the second point, x minus 2, and x minus 3. Okay, and then now the denominator you have, you take the very first point, you take 0 minus 1 again, 0 minus 2 again, 0 minus 3. Okay, so this one is just a simplification, so you can simplify it. But now there's a special property about L1. Well, first you notice that L1 is a cubic. Okay, so it's a cubic. But secondly, if you put x equals 1, then L1 just equals 0. And put x equals 2, L1 just equals 0. And put x equals 3, just equals 0. So you have this property. So L1 at 1, at 2, at 3 are equals 0. Okay. But when you put x to be the very first point, when you put 0, Then you got 0 minus 1, 0 minus 2, 0 minus 3. Then actually at 0, then L1 is equal 1. Okay. So then similarly, you can construct L2, L3, and L4. Okay. So now what is, how do you define L2? So by the same technique, how do you define L2? So tell me what is the formula for L2? Do you ignore x minus 1 and L2? Well, just write it down. Yeah, just write down. So what is L2? Can you write down something like of this form, like x minus 1, x minus 2, x minus 3? Yes, so L2 is like, now you ignore, well, but at least you got the numerator correct, right? So x minus 0, then x minus, yeah, so you ignore x minus 1, yeah, okay. So you got the idea, right? So then you get the same, you got the same method for L2. Then you can verify that L2 1 equal 1, and at all the points is just equal 0. And you can do L3 and L4. So you have 4 points. Then you have L1, L2, L3, L4. And if you plot it, okay, so L1 look like this. So L1, the blue curve, yeah, L1 equal 1 at 0, okay. And then at 1 it just equals 0, at 2 just equals 0, at 3 just equals 0, okay. Then L2 is the green one. So the green one, you see that equals 0 at 0. Then it equals 1 at 1, right? Equals 0 at 2, equals 0 at 3, okay? So it's very special polynomial, okay? But it's not the end of the story. So now we're still looking for a polynomial that interpolates the data, okay? So, okay, so this one is the L2, L3, L4. So in case you want to work it out correctly, okay? So this one, you just plug it in and, you know, the same principle here, x minus 0, then you ignore x minus 1, okay, then ignore the second point, and then similarly you ignore the third point, and so on, okay. So now the polynomial is like this. If I take L1, I multiply by 2, okay, and I plus 0 multiply L2, and then I take minus 3 multiplied by L3, and 5 multiplied by L4, then I will have a cubic polynomial that interpolates the data. So now where do I got the number 2, 0, minus 3, and 5 from? Where do I get those numbers? The values, yes, exactly. So you remember, right? So you remember the value we are given. Yeah, so the value is 2, 0, minus 3, and 5, right? So that is exactly here, 2, 0, minus 3, and 5. So now why this polynomial is the polynomial that interpolates the data? So how do you verify that? How do you verify that this is the correct polynomial? How do we know? How do we know that this is the polynomial? Yes, you plug in the value. So now what happens if I plug in the value? So remember, if I plug in the value x equals 0, okay, and what do I have here? So if I plug in x equals 0, then L1 at 0 equal 1, and L2 at 0 just equal 0. Well, it's a cubic, yes, correct, because the sum of all the cubics, yeah, and it satisfies the values. Yes, I'm checking now. If I put in the values, x equals 0, right? Then it just equal 2, right? Because L1 0 just equal 1, right? And L2 0 just equal 0, yeah. And L3 0 just equal 0, L4 0 just equal 0. So you can do the same. You see, so that is how I check that. So if I plug in 0, then I got 0 here, okay. Then, sorry, L1 0, I got 1 here. Then L0, I got 0 here. Then L3 0, I got 0 here. L4 0, I got 0 here. So I got 2. So 2 is this value, okay. So that is exactly, I mean, you can check for x equal 1, then L1 1 is just equal 0, and then this guy just equals 0, and then it just equals 0, okay. And then, so this one is how when you plot it, you plot, this is the blue curve. I mean, before, you know, you have only 4 points, yeah, 4 points and 4 values, and now you have a whole curve, yeah, that go through 4 points exactly. Okay, so that is, we call it interpolation. So any question about this one? Yes, so very nifty, yes. Okay, so you don't have to solve a linear system. Okay, so now I want to ask you something. Okay, so maybe we go to Moodle and so now suppose I go to Moodle, yes. So and then you click on the interactive documents and you click on interpolation. Okay, and you click on this one. Okay, so now we consider this as example again. Okay, but then, yeah, so but then what I show you is this is the Lagrange form of the interpolation. Okay, yeah. So how about the others? Okay, so now what cubic satisfy this interpolation condition? So which one? So can you see that? So now let me check whether you have answered this. So yeah, take a few seconds. Yes, I will check the results. So it takes a few seconds. It's okay. Let me go and check. Okay, so I can show you the response. So essentially we have one response, okay? So we have one single response, the green one. Wow, so everyone, at least 4 people. Wow, so we have two responses, five responses, but 2 answers. Okay, so you see, I mean, if you check carefully, okay, yeah, you check carefully, you will see that all 3 polynomials satisfy the interpolation condition. Okay, the third one is the Lagrangian. Okay, so we will study the other 2 cases, you know, but essentially if you expand the third one and the second one, then you get the first one. So all of the above satisfy the condition. Okay, so that is the method. You have a unique polynomial that satisfy the condition. Okay, and then secondly, I want to show you how to implement Lagrange polynomial in MATLAB very quickly. Okay, so this one I posted on Moodle as well. Yeah, so you can see that numerators is just a product of on the point x minus xs. K and k is different from j, and then denominators you just take xsj minus xsk. Okay, so this is the formula. And then how do you use this function, Lagrange function? So there is another one called test Lagrange, and you see we are given like 4 points. Yeah, so 0, 1, 2, 3, and then you define L1, L2, L3, L4, right? And then you take P to be this 2 L1 plus 0 L2 minus 3 L3 plus 5 L4, and then you run it. Okay, and we will see. I can show you the pictures. So if you run it, then you see exactly the well, this one is the 5 Lagrangian. Yeah, and then after that you have another one, which is the polynomial P. Okay, so that is how you use the Lagrange function. Okay, so you can run it. Okay, so now we go back to the slide. So now I want to generalize the process. Okay, suppose you have n plus 1 points, then you can define the Lj, okay, to be x minus xk on the top, and then xj minus xk on the bottom, and j has to be different from k, and this notation stands for the product of all the terms, you know, x minus xk, and then you can verify that Lj xj equal 1. Okay, and if I different from j, then Lj xi just equals 0. So you saw that in the concrete example already. So this one is just a general form. And then once you have the Lj, you can write out the Lagrange polynomials in this form, right? So the sum of yj Lj. So yj is the value at xj. Okay, so we now we move to the next theorem. So suppose you have n plus 1 data points. Okay, now the theorem say that you can get a polynomial that go through those data y1 up to yn plus 1, and moreover, okay, the polynomial is unique, so you can expand it, the Lagrange form, into the simplest form you can have. Okay, and it's unique. So that is the theorem, and we can show that why it's the case. Yeah, so now how do we prove that? Well, before question, so the Lagrange interpolation are different to no. So the Lagrange interpolation polynomials, when you expand it, okay, then it will be, you know, like in the Google form, you can write out in three forms, yeah. But when you expand it, it will be the same. So Lagrange interpolation polynomials is just another way of writing interpolated polynomials, but it's still the same. You know, like you say, x plus y or y plus x, still the same function. Okay, sorry, in this case, maybe like 1 plus x or x plus 1, just the same polynomial. Okay, or you know, you write x times x minus 1, or you write x squared minus x, just the same polynomial. No. LJ are different. LJ are different from PX. LJ. So if you go back to this one, LJ, okay, it's just you define it in the intermediate step. Then after that, you have to define P to be the sum of YJ, LJ. Okay, so the LJ are different from the P. Yeah. So does it make sense? So unique in the sense that, you know, I mean, so remember, if you go back to the Google form, yeah. If you go back to the Google form, yeah, so PX is the combination of all LJ, yes. Yeah, so PX, you see in the Google form, you see that PX is the third choice, okay? It is this one, it's PX. But if you expand PX, then you also get the blue form here, which is exactly the same polynomial. Okay. And so this one is the Newton form. We will study this one. And all three of them are the same polynomial. Okay. Okay, so it's good. Okay, so we can go back, yeah. So now, so before proving that, so let me remind you about the fundamental theorem of algebra. Okay. So the fundamental theorem of algebra says that if you have a polynomial of degree n, yeah, then there exists complex numbers z1 up to zn. So then you can factorize q into n terms like this. Okay, so remember, you know, I mean, if you take a linear function, it's obvious, but if you take a quadratic, you always have a complex roots, remember? So you can write out at z minus z1, z minus z2. And this is true for any polynomial of degree n. Okay, you always can factor out like this. So it's a product of n factors, z minus z1 up to z minus zn. So the z1, z2, zn could be complex numbers. So they call this one a fundamental theorem algebra. Okay. So now, so how do we prove the theorem? So existence and uniqueness. So existence is given, right? Because Lagrange form is interpolation polynomials already. So now we don't have to worry about existence. We know how to construct one interpolating polynomials. Okay. Now the tricky part is uniqueness. Uniqueness is mean that, okay, the polynomial I constructed is the only one, is unique, is unique. And now how do I prove that? Well, I just assume that Q is another polynomial, okay, of degree n. And it will, or could be less, yeah. And it will interpolate the data as well. So in the sense that, you know, if you plug in qxj, then you get yj. Okay. And so now we consider p minus q. So p minus q, if you plug in xj, okay, then by the properties that is interpolation polynomial. So you got pxj equal yj and qxj equal yj. Yeah. And j now is from 1 to n plus 1. Okay. So now the next step is, okay, so if it's 0 on n plus 1 points, yeah, then what is the conclusion? What is the conclusion? So if you have some polynomial, p minus q is a polynomial, and you know that it's 0 on xj, okay, so j from 1 to n plus 1, and what is your conclusion? Well, that's what we want to prove. Okay, we want to prove. So it needs a bit more step. We need actually, yeah. Now we have only equal at those points. Yes, they go through the same point. Yes, yes. But now we want to apply the fundamental theorem of algebra. Okay, so if you apply the fundamental theorem of algebra, okay, then you can factor out p minus q of this form. Okay. So it's a product of x minus x1, x minus x2, up to x minus xm. So because we don't know what degree m p minus q is, we just know that m less than or equal n, right? Because you take 2 degree n polynomial, when you take the difference, some terms might get cancelled, you know, like x squared plus 1 minus x squared, right? Then x squared got cancelled. So you just know that this is a degree m, and it could be less than or equal n. Okay, so then you can write down it's a product of m terms, you know, x minus x1, x minus x2 to x minus xm like this. Okay, by fundamental theorem of algebra. And then, you know, because now remember, if you plug in xn plus 1, okay, if you plug in, well, I mean, if you plug in x1, then it's definitely equals 0. Plug in x2, definitely equals 0. Plug in xm, you know, xm could be xn, then it's just equals 0. No problem. But now if you plug in xn plus 1, okay, then definitely, you know, those linear terms are not 0. Well, we assume that all the zeros are different, yeah, all the roots are different. So those terms are not 0. But we still have p xn plus 1 minus q xn plus 1 equals 0. Okay, by this interpolation condition. So then the conclusion is the constant a has to be equal 0. Okay. So the only way it can happen is the constant a equals 0. But if a equals 0, then p minus q just equals 0 for every x, right? It equals for every x. And now equal for every x, then you say that p and q are the same polynomial. Okay, so it's stronger. So before you just have it equal on finite many points, n plus 1 point. But now equal for every x, so infinite many points. And so they are the same polynomial. And so therefore they're unique. I mean, the polynomial p and q are the same. They're identical for every x. So they're the same. So it's unique. Okay. So, okay, so polyfit in MATLAB can be used to compute the interpolation polynomial of the set of data. So you can use, so before you use Lagrange polynomials, right? And now another way is you use this polyfit commands. And actually this polyfit commands, if you look it up, then it's just solving the linear system. So remember at the very beginning, you say that you can solve a linear system. So polyfit use polyfit solve a linear system to get out the coefficient. Okay, so now we can ignore that. So polyfit use the Van der Monde matrix. So let me explain the Van der Monde matrix a little bit. So now, so go back to the go back to the example here, right? So now let me share my piece of paper so it's easier to explain. Okay, so you have the data, right? So you have 0, this is x, this is y, 1, 2, 3, right? 4 points, yeah. And then you have y equal 2, 0, -3, 5, right? Then you can say that, okay, so if I let p to be ax cubed plus b x squared plus c x plus d, yeah, then I have a x1 cubed plus b x1 squared plus c x1 plus d, right, equal, so x1 then equal y1. So assume that is x1 y1 x2 y2 and so on. Okay, and you have 4 equations. Bx2 squared cx2 plus d equal y2, and ax3 cubed plus bx3 square, so this one should be square, yeah, plus cx cubed plus d equal y3, and ax4 cubed plus bx4 cubed plus c x4 plus d equal y4, right? So essentially you have something like this, and this one can be written as a linear system, right? So, and in MATLAB, so in linear system you just put in the matrix. So this one is a matrix like this. So x1 cubed, x1 square, x1 and then 1, x2 cubed, x2 square, x2 and 1, and x3 cubed, x3 square, x3 and 1, then x4 cubed, x4 square, x4 and 1, right? So you can write out a matrix like this. So A, B, C, and D. And then this one is just y1, y2, y3, y4. Okay. So this matrix, okay, has a special structure. You can see that, you know, it has the same pattern, right? Just different point, x1 cubed, x1 cubed, sorry, x1 square, x1 and 1. And you just replace x1 by x2. And this one has been proved that it's always invertible, proved by the guy named Van der Mons. So I forgot where he's from. You can look him up on Wikipedia, okay? But I think he's the first one who showed that. I think he could be a French guy. Okay? But I think he's the first one who showed that this matrix always invertible. Okay. And because he proved that it's always invertible, so they named the matrix after him. So you can prove something now and people can name after you after, say, 400 years. Okay, so just try it, just prove something. And but essentially that is why they call this Van der Mons matrix, because Van der Mons is the first man who showed that this matrix is always invertible, well, provided that all the points are different. Okay, x1, x2, x3, x4 are different points. You know, they are not the same points. Then you can solve this linear system. Okay, and that is exactly what MATLAB is doing for the polyfit commands. So the polyfit use the Van der Mons matrix to compute the interpolation polynomials. Okay, and then, well, actually you can look it up, you know, like if you go to MATLAB, you know, you say that edit polyfit. Okay, so you will see that fit a polynomial to data, and then it will show you that how to use it, but then you can read it. And actually what it does is I construct the van der Waals matrix. You see construct the van der Waals matrix. Yeah. And then once you have it, then you just solve the linear system. Well, this one just check in the parameters. Just one you have it, then you just so solving the linear system somewhere here. Solving the linear system here. Well, before solving the linear system, it did the QR factorization. So QR factorization, we did it already in the previous chapter, right? And then you solve it. Okay. So that is how they solve it. Okay, so now we go back to the slide. Okay. So you see now Lagrange form is preferred, when you try to prove something. Okay. So for example, in existence of interpolation polynomials. Okay. But every time you have a new xk, then you have to recompute on the Lj. Okay, so that is the drawback of Lagrange method. And so now Newton say that I can fix that. Now Newton say that Newton's very smart. I can fix that. Okay, so now we study Newton form. So Newton form is another method for computing the interpolation polynomials. But now Newton assumed that the data come from a function. So you assume that xj actually come from some function f, some known function f. Okay, evaluate at the data point xj. Yeah. So in many cases that is the case. Like you try to measure the wave go up and down, like on the ocean, right? After a tsunami, for example, then it's just a sine, cosine, some combination. Okay, so it's just some known function. Yeah. Then now let we do some notation. So suppose that I have Pm. Okay, Pm is the polynomial of degree at most m. Yeah, but then it go through only the first m plus 1 points. Okay, so remember you have n plus 1 points in total, but now let we do it like progressively. Yeah, so you start m equals 0 and m equals 1, then so on. Okay, and you construct Pm only interpolate the first m plus 1 points. Okay, so maybe now let me give you example. So what is P0? So suppose m equals 0. Yeah, then what is P0? So P0 interpolate only first points. It's a constant, yes, right? Because it interpolate only the first point. So actually it's just equal a constant. Yeah, so P0x, okay, is just f of x1, right? Because it's just y1, so it just interpolate the first point. And now what is P1? So what is P1? So by this definition, what is P1? Well, I mean, if you draw pictures, yeah. So now let me draw pictures. So what is, yes, it's a line, yes. But a line that goes through what point and what points? It's correct, yes. So It's a line, but a bit more precise. The line that go through what points? Go through x1 and x2. Yes, it go through x1 and x2. It's very good because by definition, if you plug in, you know, I mean, P1, right? Then it just interpolate the first 2 points. Yeah. And the first 2 points, just x1 and x2, y1, y2, right? So then it's just a line that connect those 2 first points. Okay. So, so now this is a bit more precise. Okay. So now you know that P1 is the line that go through the first 2 points. So it has the form like this: fx1 plus a constant time x minus x1, right? Yeah. And so what is a constant? So we know that P1 minus P0, you know, has degree 1, right? It's a line, yeah. And then it's go through x1, right? And then it's go through, you know, P1 go through x2, yeah. So then P1 has the form like this. It's a line that, so the line go through x1, fx1 has the form like this. Okay. But then what constant you put in here so that it go through x2, y2 as well? So what constant? So now refresh your memory. Suppose you have 2 points. No, too fast. Suppose you have 2 points, yeah? You want to make a line that go through those 2 points, yeah? Then definitely it has the form like this, because if you plug in x equal x1, yeah? Very close, but it's not quite correct. Well, I mean you. So if you remember what you have to assume that P1 x2 now equal fx2, right? And you can solve for that. Yeah. If you put in, so you can plug it in, yeah. So you plug it in. If I plug in x equal x2, then P1 x2 has to be equal fx2. Okay. So if you plug it in, and you will see that you will have well, maybe let me solve for it first, yeah. So let me go to the piece of paper. So you have P1 okay, let we put it, I put it in here. So P1x equal fx1 plus a1 x minus x1, right? So definitely you have P1x1 equal fx1 already, right? Sorry, fx1, yeah. So now what I want is I want P1x2 equal fx2, right? So that's what I want, right? And then you just plug it in. So then it's equal f of x1 plus a1 x minus, I mean x2 as x1, right? And so therefore you have equation. So you have equation fx2 minus fx1 equal a1 x2 minus x1, right? And then therefore a1 is just equal f x2 minus f x1 over x2 minus x1, right? Yeah. So that is how you get out the constant. Yeah. So you are very close, but essentially, you know, that is, and if you look a bit further, this is the slope of the line. I mean, if you plot it, so this is an x1, this is x2, right? And then this one is y1, this one is y2. So the line that go through those 2 points, this is the slope of the line. Yeah, the slope will equal the height over the difference in x. Yeah. So the difference in y over the difference in x, so it will be this one. Yeah. Okay, so what now go back to the pattern. We want to go a bit further. So go back to the slide. Yeah. So now what I want to claim is I just say that P1 is of the form fx1 plus some constant time x minus x1. Okay. And why is that? Well, because of this interpolation condition, right? So now we can go further. P2. Okay. So now P2. Yeah. Now if you okay, so equals 0 okay, and then but at least you can fix it. Okay. Okay, so now go back to this. Now I want to say that you can repeat the argument, you know, to say that P2 has the form like this. So fx1 a1 x minus x1 plus a2, the product of x minus x1 product times x minus x2. So why is that? Well, because, you know, I mean, you can repeat the argument here. Okay, so you say that P1 minus P0 now you replace by P2 minus P1. Okay, so maybe let me write down a bit more explicitly. So now I'm going to say that P2, okay, minus P1 has degree, well, now see this one is degree 2, right? Minus degree 1, right? So this one has degree as most 2, right? Because this is degree 2, this is degree 1, right? So I mean it could be, so the P2 minus P1 has degree at most 2, right? And then it's satisfied and satisfy P2 minus P1 x2 equals 0, right? And P2 minus P1 x1 equals 0. Yeah. Okay. So remember, because the interpolation condition, right? So then, you know, you can say that P2 minus P1 can be written as some constant A2 x minus x1 x minus x2. Okay. And then you flip it around. You can say that P2 is P1 plus A2 x minus x1 times x minus x2, right? Yeah. And remember, we have P1 already. So we have P1 already. We just plug it in. So P1 is f of x1 plus A1 x minus x1 plus A2 x minus x1 x minus x2. Okay. So that is, we just use the definition. We use the definition interpolation condition, right? And now that is why I say that. So if you go back to the slide, yeah, I say that if you repeat the arguments, then you can write out P2 as this fx1 plus a1x minus x1 plus a2 and the product of x minus x1 times x minus x2. And you can do the same for P3, P4 up to Pn. Okay. So Pn is f of x1, then you have a linear form like this, a1 x minus x1, and a2 x minus x1, x minus x2, and so on up to the last one. The last one is, you know, an, then the products of all the x minus x1 up to x minus xn. Okay. So I think now we take a 5 minutes break and we go back and we will I will discuss how we find the coefficient a1 up to an. But at least you saw how to find a1 already, right? So a1 is just a slope of the line, yeah. But now we want to find out a2, a3 up to an. So we stop for 5 minutes. Okay. So I will stop. I will pause the recording. Okay, so we start the lectures again, yeah. So now we agree that P0, P1, P2, and Pn has this form, okay. And this one we call it the Newton form of the interpolating polynomial. So now how do we find a1 up to an? So now before we compute a1 up to an, you know, let's give some terminology. Okay, so the coefficient a1, a2 up to an are called the divided difference of the function f with respect to the points xj. Okay, and people, or maybe Newton, he denoted by f, then open the square brackets and x1 comma x2 up to xj plus 1 and close square bracket and then equal aj. So aj is the divided difference, okay, over the points x1 up to xj plus 1. So now, you know, the divided coefficients is also the coefficient of x to the j, right, in the polynomial pj, right? Because see, if you take pn, then fn, the an is just f of x1 up to xn plus 1, right? And now, how do we compute the divided difference coefficients? So by definition, so suppose I have only 1 point, okay, then I just take the value of the function at the points. So f open brackets, close brackets, x1 is just the value of f at x1 and so on, you know. And now, so you remember that if you have 2 points, yeah, then a1, the coefficient for p1, the coefficient for x, it's just a slope of the line that goes through x1, x2, and it's just fx2 minus fx1 over x2 minus x1. So we saw that before as well. Okay, so now a1 is denoted by the divided difference over x1 and x2. Okay, so now in general you can replace x1, x2 by xj and xj plus 1, and it's still correct that it is the slope of the line that goes through xj and xj plus 1. Okay, so that is the formula here. Okay, so now the tricky part is how you compute the divided difference over 3 points. So now just take a simple case. Suppose you have x1, x2, and x3. Okay. So now maybe let me draw pictures and then I go back to the formula. Okay. So now you have 3 points. So you have 3 points, yeah? So you have x1, x2, and x3 here, okay? And now you have, say, y1, y2, y3 here. So this is y1, y2, and y3. Yeah. So essentially, you can assume that P2 is a parabola that goes through those 3 points. Yeah. So this is a parabola. So P2, right? But so now before you got to P2, remember you go through P1, right? So you go through P1. So P1 is the line. So this is P1. So P1 is the line that connect x1, x2. I mean x1, y1, y1, x2, y2, right? So this is P1 and this is P2, right? And so now remember we have the form for P1 and P2 by the notation of divided difference. So we have P1 is just f of x1 plus f of x1, x2, x minus x1, right? And P2, okay, so this one is P1x and this one is P2x. Okay, so this one is just essentially what we have been talking so far, right? So divided different x1, x2, x minus x1, x minus x2, right? But now this one is like you construct P2 from the left, right? You construct P2 from the left, you go x1, x2, then x3, yeah? But P2 can be constructed from the right, yeah? So what do I mean by that? You know, I mean like, okay, so why don't we construct P2 by first you go from x3, you go back to x2, you construct a line. Okay, so now the line is go through x2, x3. Okay, so now I forgot my red pen, but essentially you can see that. So now maybe let me label this to be Q1. Okay, so Q1. So Q1 is this line, yeah. So remember P1 is this line. P1 is you connect x1 and x2, right? But Q1 is you connect x3 back to x2, right? So P2 is still the parabola. And so now we can write out Q1. Okay. It's just f of x2 plus f x2, x3, x minus x2. Remember we construct, you know, like over x2, x3. Then you got Q1. Okay. And then P2 is now, because you construct from the right, yeah, so it will be Q1 plus f of x2, x3, then x1, then x minus x2, x minus x3. Okay, so essentially you look at the same curve P2, but you look from the left and you write out two equations P1, P2. And then if you look from the right, yeah, then you write down Q1 and P2. So because remember P2 is still a unique polynomial that go through 3 points. Okay, so you got P2 like this. Okay, so P2 now construct from X2 and X3. So now that is the slide I want to give you now. So now if you remember the pictures, now I have, you know, P1, P2, right? And Q1 and P2. Okay, so you have 4 equations. But now look at, now you look at, say, 2 and 4, right? So 2 and 4, the left-hand side are the same. Yeah. So then you can balance it. You can balance it, right? So then that is exactly what I'm going to do. And now the second observation is, so if you look at P2 in, so I moved my page up already, yeah. So now if you look at P2, yeah, you look at the coefficient for x squared, okay. Then on equation 2, then this is f x1 comma x2 x3, yeah. But on number 4, it is f x2 x3 x1. Okay, so actually they are the same because P2, you know, is the polynomial of degree 2, and so the coefficient and the x squared have to be the same. Yeah, so that is the 2 observation. Well, so the first observation is 2 and 4, you know, the left and the right hand side are the same, right? And then the second observation is the coefficient of x squared in 2 and 4 the same. So now if you equate the, I mean, if you take 1 and 3, you take the difference, okay, then it's just the form f x1 x2 minus f x2 x3 x plus some constant. Can you explain why the order is x2 x3? Okay, so now why is that? Well, because we go back to the pictures, yeah. So now my whole point is the order is not important. Okay, so the order x1 x2 x3 or x2 x3 x1, the order is not important. But why we got this order? Because if you look back at the pictures, okay, so here if you look back at the pictures, how do we got P2 in the 4th equation? Well, we got it from Q1, right? So Q1 is the line that go through x2 and x3. Yeah. Okay. So that's why you got Q1 here, right? And then you have to add on x1 at the final points. Okay. So remember in the Newton form, you know, you plug in the points sequentially, right? So here we go x1, x2. Okay, so then you construct fp1, then you add on x3. Now, actually, I think there's a typo. There should be a x3 here. Okay, to get p2, right? And then if you go from the right, you start at q1. So q1 go through x2, x3 only. Okay. Then we we have to add on an extra term x1 to get P2. Okay, so essentially we construct P2 by two approaches, one from the left and one from the right. Okay, one from the line P1 and one from the line Q1. Yeah, but then you know, even the order x1, x2, x3 or x2, x3, x1, you see that they have to be the same because they are just the same coefficient of the same polynomial. Okay. Yeah. And now I want to do some algebra. I want to do some algebra. Now I take 1 minus 3. Okay, so I say that it just equal this plus some constant. So maybe we can go back to the piece of paper and do that. So now if I go back, I take 1 minus 3. So remember, this is my 1, right? This is 2, this is 3, this is 4. Okay, so if I take 1 minus 3, yeah, then you see that on the left you got P1 minus Q1. 1 minus 3, P1 minus Q1, right? And on the right you got Fx1 minus Fx2, yeah, plus Fx1 comma x2 x minus x1 plus Fx2 x3 x minus x2, right? Okay, and then now if you just consider the x term, right? Then the coefficient for that will be Fx1 x2 minus Fx2 x3 x, yeah, and then plus some constant. The constant is just Fx1 minus Fx2 minus Fx1 comma x2 x1. No, I think this is a plus, yeah, minus Fx2 x3 x2. Okay, some constant. So this one is just some constant. Okay, and this one is the term x, yeah. Okay, so that is my first subtraction. And now that is, if you go back to the slide, that is what I claim here. So the claim is, if I take 1 minus 3, and on the left I got P1 minus Q2. Okay, and if I worry about the linear terms, then this is the linear term. Okay, and then plus some constant. And then now if I take 2 minus 4, okay, so now you just believe me, otherwise we have to spend time doing the algebra. But essentially, if you take 2 minus 4, then you got P1 minus Q1. Okay, and if you worry only about the coefficient for x only, yeah, then it will be this term. Okay, some plus some constant. So now we don't have to worry about the constant, right? Because now we have P1 minus Q1 both on the left of 5 and P1 minus Q1 on the left of number 6. Yeah, so they are the same polynomial. They are the same polynomial. Okay, more than that, they are linear as well, because remember P1 is just a line, Q1 is just a line, P1 is Q1 is just a line. So now from 5 and 6, what is your conclusion? So from 5 and 6, what is your conclusion? So remember P1x minus Q1x. So x could be any x. Okay. So what is your conclusion from 5 and 6? Yes, the coefficient of x are equal. So essentially from 5 and 6, then you have to conclude that this coefficient has to equal this coefficient, right? Because remember, it's equal for all x, so the coefficient in front of x have to be the same. And that is exactly, you know, what we want. We want, you know, to equate the coefficient in 5 and 6 for x. And then that's what we are looking for. We're looking for the divided difference over 3 points. And you see, this is the divided difference over 2 points. You know how to do it already. You know how to compute those divided difference over 2 points already. Yeah. And then you can find out the divided difference over 3 points easily. Okay. So the math is complicated, but in the end, you will see that the algorithm to compute the divided difference are very, very simple. So that is why Newton is a genius. Okay. So now the proof, okay, it's a bit tedious, but once you got it, then you will see that, you know, I mean, the computation is very simple. So now if I replace x1, x2, x3 by xj plus 1 or xj plus 2, then I have the same formula. Okay. So the formula doesn't depend on the index. So if I got xj plus 2 over 3 points, divided difference can be computed by divided difference over 2 points, xj plus 1 over xj plus 2 minus this one over xj plus 2 minus xj. Okay. So now, using the same method, we can prove, so it's a bit tedious, but you can prove that divided difference over 4 points can be computed by divided difference over 3 points. Okay. So now you take 2, 3, 4, the last 3 points, yeah, and take the first 3 points, yeah, so 1, 2, 3 here, and then over the last point x4 minus x1, the first point, yeah, okay. And then by induction, you can prove the divided difference over k plus 1 points, okay, so we skip that. And then by that, we have the formula for all the divided difference coefficients. Okay, so now once you have the formula, okay, so actually the computation is very simple. So now you write a table like this. You write x1, x2, x3, x4. And the next column, you write fx1, fx2, fx3, and f4. Well, we assume that we know those values. Then you can compute the divided difference fx1, x2. So remember, you just take this number minus this number over x2 minus x1, okay? And so on. So you have divided difference over x2, x3, x3, x4. And once you have the third columns, now how do you compute this one? Well, I just take the difference over fx2, x3 minus fx1, x2 over x3 minus x1, okay? And so on. So by the end, you can compute the whole table easily. And actually, I have implemented a MATLAB to compute this divided difference table. So maybe we do the, and then you see on the red coefficient now, yeah, on the red coefficient will form the Newton interpolation polynomial, right? So remember the formula for Newton polynomials, okay? So now we do an example. So suppose you have the very first example, we have x equals 0, 1, 2, and 3, yeah? And then you have y equal 2, 0, minus 3, and then 5. Yeah. So how do I get a number minus 2 here? Well, I just take 0 minus 2 over 1 minus 0. Then I got minus 2 here. Okay. Similarly, if I take minus 3 minus 0 over 2 minus 1, then I got minus 3 here. Okay. And how do I get 8 here? Well, I just take 5 minus 5, so become 8 over 3 minus 2. So give me 8 here. Okay. And now how do I get this minus 1/2? Well, minus 3. Okay. Minus 2. So become minus 1, right? Divided by 2 minus 0. So give me minus 1/2. Okay. And so on. So this one is, I take 8 minus 3, so become 11, then minus 3 minus 1, so 11 over 2. And for number 2 here, you just take the difference of 11 over 2 minus 1/2 over 3 over 0. Okay. And then when you have all the red coefficient, yeah, then you plug in the Newton polynomials here. So 2 is the first coefficient here, yeah. And then minus 2. So minus 2 is here. So minus 2 is here. And remember this one just x minus x0. Sorry, this one is just x minus 0. Okay, what is just x? Okay. And then the second one is minus 1/2. So you got minus 1/2 here. Okay. And the product of x minus 0 and x minus 1. And the last one is 2. So you got 2 here. And you got a product of x minus the first point, x minus the second point, and x minus the third point. Okay. So it's very simple to compute the divided difference table. Once you have it, once you have the formula. So once you prove it. Okay. So now, so that is this is a MATLAB function to compute the divided difference table. So look at what it does. So the x data and the y data are given. Okay, so x1, x2 up to xn, y1 up to yn. Okay. So now if you look at this, program, yeah, then how do you get the divided difference at the end? So remember your divided difference table look like this, look like a triangle like this. Okay. But in MATLAB, you cannot implement the triangle like this, right? I mean, you just have an array, two-dimensional array. So then what position in this array T so that I can get my coefficients? Well, maybe the best way to do it is maybe we try an example, okay? So let me go to MATLAB and we try this example, yeah? So now in MATLAB, I have this already, so help DD, okay? So now if I put in my, so remember my data point. So the X data is just 0, 1, 2, and 3, right? So that is my X data. And Y data is, so remember the example. So example is, so So 2, 0, minus 3, 5, 2, 0, so 2, 0, minus 3, 5, yeah. So now I just type t equal dd x data y data. So now where is the divided difference coefficient? 2, 0. Okay, thank you. So y data is 2, 0, minus 3, 5. Yeah. Okay, thank you. So then my divided coefficient will be like this. Okay. So do you see where the divided coefficient come from in the table? You see, so the x equals 0 here, x equals 1 here, x equals 2 here, x equals 3 here. Okay. And then this is y equals 2, y equals 0, y equals minus 3, and y equals 5. Yeah. So where is my divided coefficients? So where is the coefficient? In the table T. Anyone? Where can I find the divided difference coefficient? In the table T. The top row, yes. Now you can see it. In the top row, you see that 2, minus 2, minus 0.5, and 2, right? Adjust the divided difference coefficient. So if you go back, we playing around with this example in a few examples already. So if you go back to the, well, let me go back to the slide. Yeah. So in the top row, you see that the divided coefficient is 2, minus 2, a half, and 2. So in the sense that, you know, the MATLAB cannot implement these triangles, yeah, and it push back on the columns upwards, yeah. Then you can see that it's like a table T is like a, you know, not an upper triangular, but it's like a triangular matrix, yeah. So then the top row will give you the coefficient, okay, of the divided difference table. Yeah, so this is, well, I mean, you have to go through the loops, but essentially the loops will do exactly what we did for the divided difference table. You know, this Tij, okay, so please check the index. But this one is just a double loops, yeah. So Ti plus 1 j minus 1 minus Ti j minus 1. So you see, then over, you know, the difference point here. So you see, this is what I just did here. So if I apply the DD script, then I got this table, and the top row give me the divided difference coefficient. Okay. So this one is another example. Okay. So now suppose I have a function f. Okay. And I have the values of f of x. You know, some values like this of 1, 1.2, 1.4, 1.6. So now use the linear or a cubic interpolation. You estimate 1.3. Okay. So now if you use linear interpolation, it means that you just make a line that go through 1.2 and 1.4. Okay. And then this is the equation of the line. Yeah. So we just skip the calculation. And if you plug in the value at 1.3, okay, so you plug it in and you get something like this. Okay. And now if I want to use a cubic, then I form a divided difference table. Again, this one, you can plug in DD, then you get out all the coefficients. So the first coefficient here, you put in here, okay. The second coefficient 0.699, you put in here, okay. And do not forget to multiply by x minus the first data point, okay. And now your next coefficient is minus 0.375, so minus 0.1375. Then x minus the first, x minus the second point, yeah. And then the last coefficient is here, 0.05, okay. And then you multiply by x minus the first point, x minus the second point, x minus the third point, okay. So we don't use the last point, okay. We don't use the last point, okay. So in the Newton form, you know, there is no last point, so just x minus 1.4 and you stop it. And then now you plug in at 1.3. So you see that a cubic, right? When you plug in 1.3, give you 0.286, and the errors is smaller, 10 to the minus 5. So remember before, when you use linear interpolation, well, 0.28, we didn't compute the errors. Okay, but you know, I mean, essentially when you use cubic, then you get a better approximation. Okay, because 0.86, so this is the exact 0.86, and this one 0.82, right? So the difference up to the third digit, yeah. So the cubic is better approximation. So Hermite interpolation. So Hermite interpolation is, well, so we now we move to a new type of interpolation. Okay, so this one we talk about Lagrange, we talk about Newton form, but both methods you have only the data and the values of the function at the data points. Okay, but there is another form of interpolation when they give you a derivative as well. Okay, and they call it Hermite interpolation. So named after the first guy who proposed this this problem. And now in this case, then not only the values but the derivatives are given as well. So this one, the J here is just a derivative from order 0 to order ki. Yeah. So in this case, the total number of conditions on P will be, you know, n plus k1 up to kn. So ki is the you know, the number of derivatives you have for each point. Yeah. And then we don't prove it, but there exists a unique polynomial of degree m-1 that satisfy this Hermite interpolation condition. Okay. So now suppose we do a simple example. Suppose you find a polynomial that have those three values. So P0 equals 0, P1 equals 1, and derivative P prime 1 is equal to. So first, what is the degree of this polynomial? So what is the degree of this polynomial? Anyone? degree 1. So why is degree 1? So degree 1 is just a line, yeah. So good point. Derivative is a constant. No. But derivative here, derivative evaluated at 1. So derivative here is only at 1. So we don't know whether it's the constant at every point, yeah. But you see, I mean, we have three equations, yeah. Just mean that we have 3 unknowns. So if we have 3 unknowns, then the polynomial should have 3 coefficients, yeah. It has 3 coefficients, then it has to be a if it has 3 coefficients, then what should it be? A second degree, yes, second degree, yeah. So just a parabola, okay. So now, so you suppose that now you try to solve it. So now I just take, you know, my p to be a x squared plus bx plus c, right? And I have 3 conditions. So p0 equal 0, p1 equal 1, and p prime at 1 equal 2, right? And so you can see that p0 equals 0, then if I put in p0 equals 0, yeah, then I put p0, I put 0 here, 0 here, I just have c equals 0, okay, and p1 equal 1, so I just put in p1, then I got a plus b plus c, right, equal 1, but remember c equals 0, so I just have a plus b equal 1, right? Then p prime, so now what is p prime? So p prime is just 2ax plus b, yeah, so p prime 1 just equal 2a plus b, okay, and equal 2, right, by this condition. So now you have a plus b equal 1, 2a plus b equal 2, right? So you got, so this one is like 1 and 2, so 2 minus 1 is give you a just equal 1, and b has to be equal 0, right? So then you just have p just equal x squared, right? So it's a bit boring, but this is what it is, yeah. So okay, so I mean this in general, I mean this could be a bit complicated to solve a general problem, but at least for this case, you know, you can solve it by direct method, by putting the values. So what happens if you have only one node? What happens if you have only derivative only at one point? So there's a special name for this. So go back to this, yeah. Suppose you have derivative at only one point, okay. Then there's a name for this polynomial. So maybe let me write down maybe a bit clearer. So suppose you have only derivative at one point, yeah. Then you have like p. Yes, it's just a Taylor expansion. Yes, very good. So just a Taylor expansion. So you just have x minus x0 to the k. You know. So this is the Taylor polynomials. Okay. So we are not going to study this further, but at least you know that if there is one point, then it's just a Taylor polynomial. And that is a special case. Okay, so we are not going to study Hermite polynomial further. Okay, so now go back to the Lagrange interpolation. So now what I want to discuss is about the error. So remember, you know, you have the interpolation condition. You just have the values at the point x1 up to xn plus 1. Okay. But now, you know, what happened at other points? So at other points, we don't know. At other points, we don't know. And we say that is the errors. Okay. So the error function en is defined to be the difference between the original function f minus the polynomial Pn. Okay. So if you can estimate En in absolute values, then you can approximate the value of the errors of the Lagrange interpolation. Okay. And you see that, you know, I mean, the errors function has the property that if you put in x equal xj, then the error just equals 0. But at other points, you don't know, right? Okay, so now there's a theorem. So the theorem is now suppose, well, before I give the theorem, yeah, I say that a function is in CR. So CR, just C stands for continuous, and R is some order, right? So if you have the function f, the first derivative, the second derivative, up to the R order derivative, okay? So all those derivatives exist and continuous. Okay, then we say that the function in CR. So just the definition. So the theorem say that, okay, so now suppose the function f is Cn plus 1. Yeah. So at least it has derivative up to order n plus 1 on the intervals x1 up to xn plus 1. Okay, so this one is just the whole intervals. So you assume that you order x1, x2 up to xn plus 1, sorry, x plus 1. Then you make the whole intervals. Okay. Then for any x in the interval from x1 to xn plus 1, then the errors, okay, is given by this formula. And here, so you notice that, you know, first xi, okay, xi is just some number, unknown numbers. But you know, this unknown number is in the interval x1 up to xn plus 1. Okay. And over n plus 1 factorials. And secondly, you have a product x minus x1 up to x minus xn plus 1. And you see, if you put in x equal x1 or x equal x2, then the error is equal 0. So it's an interpolation. So right at the interpolation point, the error just equals 0. But outside the interpolation points, then it takes a form like this. Okay, so that is the theorem. So how do we prove this theorem? So proving this theorem is a bit tricky, but you can prove it in 2 steps. Okay. So the first step is we prove the mean value theorem for divided difference. Okay. So the mean value theorem for divided difference just say that if you have x1 up to xn plus 1, the function is derivative up to order n, then there's a point xi, so that the divided difference coefficient over x1 up to xn plus 1 is a derivative of order n, some point xi over n factorials. Okay, so now let's see whether this theorem makes sense or not. So I mean, if I take, what happens if I take only n equal 1? Okay, so what happens if I take n equal 1? So this means that I have only 2 points. Okay, so let me write down this theorem in the special case. So the theorem in the special case can be written like this. So suppose I have x1, right? Less than x2. Okay. And then my claim is f of x1 comma x2 will equal, so remember here n equal 1, okay? N equal 1. F prime, because n equal 1, xi over 1 factorial. Okay? And xi is in x1, x2. So have you seen this theorem before? Have you seen this theorem before? Okay, so maybe let me write out a bit more explicitly. Okay, because it's a divided difference, yeah. So if you remember the formula for divided difference, so this one is just fx2 minus fx1 over x2 minus x1 equal f prime xi is x1 comma x2. So I have, yes, the mean value theorem. Yes, mean value theorem. Yeah. So you see, so this is a mean value theorem. For 2 points, it's just a mean value theorem. Okay. But now what happens if n equal 2? So n equal 2. Okay, so that's why this one has a name mean value theorem for divided difference. Okay. So n equal 2, then I have fx1 comma x2 x3. Okay. Equal f double prime xi over 2. Well, 2 factorial just equal 2, right? So xi is in x1 comma x3. Okay, so this one may be a bit tricky, right? Maybe we haven't seen this theorem before, right? So now we have to prove it. Yeah. But well, before we prove it, so let's go back to the case here. Yeah. So now maybe let me. So how do we prove? So this case we don't have to prove, right? N equal 1 we don't have to prove. This one just a mean value theorem. Now n equal 2, right? So n equal 2. Now we just take. Suppose I have a polynomial P2. Yeah. And it interpolate x1, x2, and x3. So I assume that I have a polynomial like this. Okay. So P2 are the same. I mean, not the same, but P2 interpolate at x1, x2, x3. So if you put in x1, x2, x3, I just give the same value at fx1, fx2, and fx3. So assume like this. Okay. So now, if you remember the Newton form, yeah, then I can write down P2. It's just f of x1 plus the divided difference x1 over x, I mean x1, x2, x minus x1 plus f and divided difference over x1, x2, x3, x minus x1, x minus x2, right? Yeah, got it? So far so good, right? So now let me consider this function. Now let me consider this function, yeah. So I consider this function g. So g will equal f minus p2. Okay. So what is special about function g? Well, g of x1, right, will equal f of x1 minus p2 x1 will equal 0, right? And similarly, gx2 equals 0, gx3 equals 0, right? Yeah. So now what does the function g look like? So if you have x1, x2, x3 like this, then definitely g will cross through. So this one is suppose OX, yeah, OX. Then definitely g will cross through those 3 points somehow. Okay. So now, if I consider the mean value theorem for g, yeah. So now I consider the mean value theorem. So this is a mean value theorem for 2 points. So mean value theorem. So mean value theorem. So MVT stand for mean value theorem for g. Okay. Then there is say y1. Yeah. So there is so I will say that it will be g of x1 minus x2 over x1 minus x2 g prime at y1. Yeah. So this is a mean value theorem, right? No, nothing new here. But what is gx1? So remember gx1 equals 0. Gx2 equals 0. So 0 minus 0. Yeah. Just equals 0. So g prime 0 is just equals 0. So just equals 0. Okay. So, and then similarly, you have g prime y2 equals 0, you know, so this one is for g x2 minus x3 over x2 minus x3. Okay. Yeah. So now I have g prime. So this one is a function g, right? Yeah. So g prime. So g prime equals 0 is like you have this, the slope here equals 0. Yeah. So you have, so g prime. So now I just have, this is my y1. Yeah. This is my y2. Right? When the slope equals 0. So this is my y1, y2. So now I just have my function g prime. Look like this. So this is g prime. Yeah. But now I apply mean value theorem again. Okay, for g prime. Yeah. Then I got, say this one is z. Okay. So then I have 0 equal g prime at y2 minus g prime at y1 over y2 minus y1. Yeah. Equal g double prime at some point z. Okay. Agree, right? So this one just mean value theorem again for g prime. Okay. So now what is the next step now? So now my claim is g prime double z, g double prime z is just equal 0 for some z in, you know, the biggest interval is x1, x3, right? But now remember, what is my g? So my g, if you go back to the beginning, g is just f minus p2. F minus p2, right? And f, well, we just write f here. But p2 is something, you know, I mean, you don't worry about the lower terms, but the last term will be, you know, dot, dot, dot. I just write the lower terms. Yeah, but the last term is fx1, x2, x3, x minus x1, x minus x2, right? So why I say that? Well, because, you know, if you take the second derivative, so this one will become g double prime, say at z, and this one f double prime at z, yeah. And then because those values. I mean, there will be either constant or linear terms. When you take second derivative, it just goes away. Okay. And then this one, what remains is only this term. So you got -2 of f x1, x2, x3 and equal 0. And essentially, you just prove it. So you just prove that f x1 comma x2 x3 just equal f double prime z over 2. Well, I mean, before we say xi, there's a point xi, but essentially that is how you prove it. So 3 o'clock already, so we stop here, yeah. So I stop the recording and you can ask me question. So at least I prove